Well, so let us start our discussion today on induction motor. So, in induction motor, or rather, I would like to uh, describe it as induction machine because not only motor, I will also discuss induction generator here. But obviously, and somewhat in a different way, like what we did is for synchronous machine. We first started with synchronous generator and then we started considering synchronous motor. Here I will consider first the induction motor and then I will consider induction generator, right? So in first, if we talking about induction motor, which one was very popular for many of its practical application and rugged construction. Uh, Induction motor, you can study that there are two types of induction motor is possible. One is slip ring induction motor, another one is squirrel cage induction motor. So, what is the difference between slip ring and squirrel cage? Let me show you the structure of rotor that will make you understand. Just a minute. So here also I would like to say one thing that like our synchronous machine, we were having two different types of machine based on their rotor structure. One is cylindrical rotor machine, another one was salient pole machine. And here also the stator structure remain more or less same like that was for our three-phase stator, but the rotor structure is slightly different, and that different in this rotor structure is in terms of two rotor. Here you can see that one is slip ring rotor, another one is squirrel cage rotor. The squirrel cage rotor, these are the rotor bars and they are solidly shorted by an end ring, and this one is squirrel slip ring rotor. Slip ring rotor is uh, the fundamental difference between slip ring and squirrel cage. If you ask me to draw, I can show you. In case of slip ring, it is like, in case of first, let me draw the squirrel cage first. This is the end ring. Now, So in reality, what happens that these bars, this is the structure for squirrel cage. These bars are conducting bars and made up of these end rings are used to short them. Sometimes avoid undesirable mechanical characteristics of machine. We do skewing of this bar. Like instead of using this straight bar, what we do, we use a kind of tilted or skewed bar. And what is there for squirrel cage induction slip? This is for squirrel cage. And for slip ring, what you can get is that you can have means here it is clear for you that the rotor structure is solidly shorted. But in case of slip ring, it is not shorted. It is one end is shortened and the other end is accessible. There is a three-phase, generally three-phase winding is present over this rotor structure, and they are accessible to outside through these slip rings. These are the three slip rings you can see for these three different phases. So instead of you will have a choice. You can short them directly, or you can insert additional resistance, reactance, or any additional electric circuits. Even you can connect some three-phase power source with that slip rings. That will be your choice. Uh, Without means making it means without discussing much on this structure of the machine, because structure of the machine you will get several videos, and I will send one or two videos to your CR also, so you can, and I think I have already sent a few videos when I discussed fundamental of rotating machine, because if you want to understand structure of a machine, you must observe or means watch a video. There is no other better way to understand the construction of a machine rather than watching a practical video where someone is dismantling a machine in a workshop. But if I keep you means if I trying to deliver you a lecture on this machine construction, it will become extremely boring. But it is not my objective to make you bored, although I means have been doing it for last almost 7-8 months, but means that is not intentional. It was kind of accidental. So what I am trying to say that this here, what we want, that we need uh, if those who are interested in construction, they may go to that and watch those videos. I will supply another few videos, and here a few interesting points, those are not maybe mentioned in the videos, and the analysis part is very very important. So what is the analysis part? Here few things I would like to clearly mention, that first of all, it is not required to have same number of phases on the stator and rotor winding. This is one point. Another point is that it is mandatory Now, as the squirrel cage, basically these are a few conductor bars shorted by two end rings. So here, the flexibility of squirrel cage is that it can adopt itself, like suppose you are having a four-pole machine. Four-pole machine, accidentally you one day your stator burnt out. Now you can means four pole squirrel cage induction machine. Now you can take out the rotor if you find the rotor circuit is healthy and intact, and if the rotor matches the mechanical dimension of another stator having 6 pole, 8 pole or 10 pole, you can easily place this rotor, which initially was installed inside a 4 pole machine, inside a machine that is having 6 pole, 8 pole or 10 pole. You can easily place it there. There will be no harm, no confusion. Why? Because your rotor is means quite flexible to adapt itself for any number of poles. First of all, why number of poles must be same? That is the one question. If you recall the rotating MMF, that rotating MMF produce a few number of poles. If you go back to my lectures on fundamental of rotating machine, then you must observe that when we feed our stator winding with balanced supply, and then that balanced supply produces a rotating magnetic field. That rotating magnetic field always defined by either 2 poles, 4 poles, 6 poles. Means what I am trying to say, that means by that is a fixed number of poles we need to mention to define the characteristics of that rotating MMF inside our machine. Now, if that is the case, then think about this kind of structure. This can adapt to any number of poles. But if you consider a slip ring machine, which is providing you external access, and thereby it means when you want external access, you are actually also compromising on the flexibility of rotor structure. The rotor doesn't remain flexible, and if suppose the rotor for a slip ring machine where you have external access, the rotor was initially designed for 4 poles, and now if you try to fix that or put that rotor inside a 6 pole stator structure, what would happen? That 6 pole structure and this 4 pole rotor won't match, because the stator will always produce a 6 pole rotating MMF, and that because whatever be your motor machine, irrespective of any machine, it is always two-way. If anyone asks you that, just in a single sentence express the fundamental of torque production. So the fundamental of torque production is that either few things, if you remember, then that will help you to understand and means explain all the motor active means actions. One is magnetic field lines are like stretched elastic rubber band. They always try to means restore the minimum energy path. So, and that minimum energy path, if you recall your last semester class, all the energy storage takes place across air gap. So in other way, we can say if we reduce the amount of air gap, the amount of energy in that circuit. We can able to reduce the amount of energy in that circuit. Now, if that is the case, then like for all the machine that is having difference or variation in reluctance path, there you can like the machine magnetic structure will always offer, or means not magnetic structure, rather the flux lines will always find a minimum reluctance path, and whenever they will be means they will feel a compulsion to pass through a path that is not having minimum length, they will try to bend that path in such a way so that they can avail minimum reluctance path, and by doing so they produce torque. This is for single excited system, like only you are producing magnetic lines of force through your stator and or through your rotor, and either the other end, either the stator or the rotor is means relaxed. There is no supply on the other side, but there is some means the iron structure or the reluctance path is not even, and the motor is trying to, means not motor, rather the flux lines are trying to stretch it, or means in such a way that it get the minimum reluctance path, and that generates a torque. Now another kind of things what you can have is that both of your rotor and stator stator are having even structure. There is even reluctance across all the points on the outer surface of your rotor and inner surface of your stator. But what you can have is that due to your magnetic means you are giving current to your both rotor and stator, but there is some magnetic interaction between the rotor current and stator flux, and that causes either magnetic interlocking or magnetic means kind of repulsion that produces the torque. In case of synchronous machine, it is the magnetic interlocking that makes your rotor rotate. In case of DC machine, it was what? It was kind of torque that was trying to repel, means not repel, rather trying to displace your rotor from one position to other, and rest of the things are done by the inertia, that is following the Barlow-Wills principle. And what is here in case of this this induction motor, it is also a kind of single excited system, but this works in a unique way. It means transfers that part of this electrical energy to its rotor, and then rotor starts producing its own magnetic field, and thereby it gives us a kind of like magnetic interlocking. In a nutshell, it is like you are having means we often consider induction motor. Long back one student asked me that, said, why are you claiming that synchronous alternator is generalized transformer? Because he read it somewhere that induction machine is also a case of generalized transformer, and it is true that in induction machine we provide the supply to our stator, and this rotating MMF sweep across our rotor. This kind of structure is there, like this So these rotating EMF sweep across the conductors and thereby they some EMF gets induced across these rotor conductors or rotor bars, and as this EMF seat of this EMF is a closed path, so this EMF causes a flow of current, and that current produces another set of magnetic pole. Now if these two poles are not matching, then there will be top pulsation, and that is not acceptable. So that is why we must then think about one thing, that we can have different number of rotor and stator, but they must be having equal number of poles. Even if you are not getting it, let me try to give you a transformer analogy. Suppose you are having just a minute, let me complete. So this was the diagram for our Scott connection. If you can recall, it was A, C and B. So here it was clear that we can have this was three phase, this was two phase. However, if you compare these two, then can you tell me how many physical transformer were there? Two physical transformer were there. So if there is two physical transformer, that means you are having two magnetic circuit, and as long as you are connecting two balance supply here, two balance load here, suppose here you connect R, here also you connect R, you would get a balanced current drawn from this phase A, B, C. But once if you think one situation, if you like this three phase to two phase is, that means what I am trying to say, that transformer rotor and stator must not have same number of phases. They can have independent number of phases. But what would happen if you have one machine having iron core, one transformer having iron core, and the other transformer is like means this, that means this is working on two mm, right? Now what if I tell you that do not use this phase? Actually these two phases are electrically 90-degree apart. If you consider the Scott secondary side, 90-degree apart. Now if I ask you that don't do this, instead of doing this, you do what? You take means an inductor, a large one, and you connect it across this, and keep it open. The inductor value is so chosen that for given frequency XL is equal to R. But now do you think what it was when we were having R connected across both phases, and now across one phase we are having R and L, the situation remains same. Obviously, it is not. The system will behave like an unbalanced system. But why? Because you are not able to produce the balanced MMF condition. Previously, the balancing was achieved in terms of MMF, not in terms of phase. So, by extending the same analogy, you can understand that in case of three-phase induction motor also, it is important that number of poles between stator and rotor must be same. However, phase we can have different phases, like here we are having different number of phases. Now, as our transformer operates with constant flux, if we consider that our induction machine is also working under constant flux condition, and you can easily understand it, there is machine terminal, it produces a rotating magnetic field that rotates in space at a speed of synchronous speed, and when that synchronous speed that cuts the rotor structure, that rotor is made up of solid iron. Actually, all these animations I have taken to make it more easy for you to understand. This is the rotating magnetic field. Now when you place this kind of change in flux associated with them, and therefore an EMF will be induced, and that EMF will, because these yellow color conductor bars are shorted by this end ring, there will be a flow of current through them, and that current will produce a torque so as to make these things rotate. That if this is the, actually this is how we are having this rotating magnetic field, and that causes a flow of different current through our rotor conductors, and the whole rotor conductors carry almost a sinusoidal current. If you consider their resistance is very small in that rotor bar, they are carrying almost a sinusoidal current, and that current is the nature of that current is such that it tries to oppose the very cause of its production. So that current interacts with the flux that produces it, and it produces a torque to speed up the rotor, and that rotor tries to align itself with the rotating magnetic field. So if we try to write the statement for the torque production, it is like stepwise. One is three-phase AC balanced This is step 1. Step 2, the conductors of the rotor bar experiences flux variation initially stationary conductor uh, of the rotor bar experiences flux variation. Third stage will be, due to this flux variation, an alternating EMF will be induced across rotor conductor. As the rotor circuit is closed, the induced EMF will cause a flow of current. Do note that this EMF, this induced EMF, is not a conventional back EMF that generate in your DC machine due to that is in DC machine what we notice as a back EMF is a dynamically induced EMF, and here what we are getting, this is an EMF induced due to your magnetic field interaction. So this is not induced due to dynamic action. In case of your synchronous machine, that is also a dynamically induced EMF. But in case of your induction machine, this EMF is means induced due to transformer action. This statically, more or less, it's statically induced EMF. Now, this current, how this current will work? This current that will try to oppose the varicose And what is the varicose? The relative speed between rotor bars or rotor conductors and rotating magnetic field. So produced by the stator winding. Rotate in the direction like those currents, they interact with the rotating MMF flux in such a way that it produces a torque to oppose the varicose of the current and thereby producing a torque in the same direction of rotating magnetic field and try to reduce the relative speed between rotor conductors and rotating magnetic field. However, and slip S is defined as so this slip is very important because if slip is small, so how we define this slip, that is in terms of pole we can write it like this ns is equal to what, these are is equal to, like we multiply both side with p, and as I have mentioned that rotor number of p is equal to the stator number of p. So ns and nr will give us their corresponding frequency. Like if these are in rpm, then we do one more manipulation like p ns by 120 minus p nr by 120 by p ns by 120, and then it will give us fs minus fr by fs. and this one is basically our rotor frequency. So rotor frequency will be, we can write it like F2, and so rotor conductor current frequency is F2, and rotor mechanical structure frequency is Fr. All is in hertz. Now it is clear that if you do this, F2 is equal to what? This F2 is equal to SFS, and Fr is equal to 1 minus SFS, and if you add this F2 plus Fr, then you will get SFS plus 1 minus SFS, that is Fs. The importance of this statement is that although your rotor current frequency is very small with respect to your rotor structure, the rotor current frequency is the relative frequency, or the differential frequency, better to say the differential frequency, and rotor current frequency is the differential frequency, and that differential frequency in running condition, when the motor is in run, is the rotating element frequency minus the mechanical rotor structure frequency. But with respect to a standstill frame, your rotor frequency is that F2 plus Fr, that is Fs. Like, although the rotor current or rotor induced EMF, their frequency with respect to the rotor rotating structure is F2 or SFS, but it is with respect to a standstill reference frame, it is Fs, which is same as your supply side or stator current or voltage frequency. This is a very important statement, because why this is important, that I am going to discuss. Now, so this is one more thing. Now point number 8 is that so at start slip S is equal to 1, at when the rotor attains synchronous speed, however, the EMF induced across rotor, its current frequency is directly proportional to this S, and once your rotor reaches synchronous speed, there will be no current flowing through the rotor bar, and therefore the torque will become zero. it will produce zero torque. Now, if the torque becomes zero, then what would happen? Then uh, the and consequently it will execute or it will undergo mechanical retardation and hence it will undergo mechanical retardation and sleep yes will again become greater than 0. So sleep cannot be 0 for our induction motor action. Now, this induction motor, this rotor can be viewed as the secondary side of a transformer, and that one is the stator is like the primary side of the transformer. So, what we can do is that we can try to develop the equivalent circuit based on this. Now see that here I would like to develop this. First, we will consider the simple as theory with some approximation and assumption, and then we will go to more realistic case. So here my assumption is development of induction machine theory based on constant mutual flux. So what is that constant mutual flux? Is that first of all three-phase primary winding. Now, however, what you can see here, transformer leakage or means transformer reactance is Okay. Okay. Just a minute. Before I go to this point, let me, if we try to develop it, a similarity between transformer and in that analogy of transformer, if we try to develop this theory, then another thing, like told you the example of Scott transformer. Here you can find out that rotor winding, it is analogous to the secondary winding of your transformer. However, in rotor winding, there is the mechanical load will cause an change in slip and suitable modeling So mechanical load, obviously in line with that previous discussion of parallel operation and prime mover of a synchronous alternator, you can understand that when we are talking about active power, even in case of alternator, active power change was need to be supplied by, or means active power requirement is taken care of by the prime mover. Your field winding cannot do much in terms of active power. Field winding current cannot do much. I'm talking about synchronous alternator. Now, alternator converts mechanical energy in electrical energy, and electrical active power require mechanical input, mechanical prime mover input. Now, when we are talking about induction motor that converts electrical energy into mechanical energy. Now, if we are talking about mechanical load, that means that mechanical load can suitably be modeled by its by a component of electrical engineering, that is that can represent active power. So among our R and C, our R can only represent active power. So this variable mechanical load applied on our induction motor shaft can be viewed as a variable rheostat connected across our secondary of transformer. How we'll discuss. Now here one more thing that is there. During start, your induction machine rotor like secondary short circuited. Rotor winding is analogous or short circuited secondary winding. Then point number 5, that the difference of means transformer there exist in transformer by this air gap. I am mentioning any means the gap between your primary and secondary winding. If you watch transformer construction video, you will find that generally low voltage winding is wound on the limb of the transformer, because limb or the core is, we are going to arc the core, so that will always be in arc potential, and low voltage winding is placed adjacent to our core, and on that low voltage winding we place our high voltage winding, but there is a very thin gap, and sometimes this is filled with air and sometimes it is filled with other means materials. But whatever be the amount of gap, that is very small, and if we apply our common sense, we can understand that in case of induction motor, when one part is having, we are having a movable part, that is the rotor, so we cannot place rotor and stator so close to each other like we place the primary and secondary winding of the transformer. So in induction motor we have a large air gap. So if air gap is large, then what would happen? That means if we try to model the magnetizing current is large for IM. IM means induction machine. In addition, if you are considering the leakage flux, what we know, leakage flux is proportional to stator current. This is true for induction motor and transformer also. For both of them, the leakage flux is proportional to stator current. Therefore, the assumption, now in case of transformer, this in case of induction motor, leakage is high, leakage flux is high. Therefore, mutual flux, that is what means gross minus leakage is not constant like the transformer. The point here is that in case of transformer you can observe a very small variation of mutual flux due to leakage flux, because in transformer leakage is very small. But in case of three-phase induction motor, due to this large leakage, what you will have, for different value of stator current, you will have different value of leakage, and that leakage is not means something that is like you can neglect it, or the leakage value is not very insignificant, but it causes somewhat I won't say it's tangible, but some change in mutual flux takes place in case of induction motor also. However, for an ergonomically designed induction motor, this flux change is within the band of 2 to 8%. This change in mutual flux so there is no harm even if you consider 92% as 100% for ease of your calculation and making it understandable. So first we will consider, based on constant mutual flux, the analysis that we did for transformer, the approximate equivalent circuit, and then we will discuss the exact equivalent circuit, and based on that we will have two different circle diagrams, and here the circle diagrams are very important. One is for approximate equivalent and another one is for exact equivalent circle diagram, right? So in my next video I will discuss that.